Hi, I'm Jim Heffron. These are my lessons in Calculus 2. So, starting a new chapter, and very exciting for two reasons. One is that it's the final chapter, so that's we're well on our way. We're finishing up. We're almost there. The second reason is that, to be 100% perfectly frank, is much easier than the chapter that we just did. So that's a good thing. Everybody welcomes a break. So let's get to it. Okay, very good. So let's see here. We're doing vectors in 2D and 3D, and it's been my experience that many folks in the room will have seen much or all of this, maybe in a high school physics class, for example. And we have to make sure, our goal here is to make sure that everybody's using the same words. Sometimes a person has seen somewhat different notation, or seen some of the words and not others of the words, sort of stuff. And so we're just making sure everybody's on the same page. Okay, great. So we'll start with 2 dimensions, and you won't be surprised to find that after a little bit we'll go to 3 dimensions. So the motivation takes us back to Newton and Leibniz thinking about planets going around the sun. You imagine a particle whose motion along the curve is described somehow by a parameterization, just like you had a planet going in an orbit. We most naturally describe its instantaneous rate of change by using a magnitude and a direction. So here we are at x equals a, and we've got it's got some speed there, maybe 35 miles an hour or something, and some direction, sort of a little bit to the southeast or something. Okay. So displacement consists of a magnitude and a direction. And one technical point is that the zero displacement has length 0, but it doesn't make sense to give it a direction. On the left below, I have a 2 over and 1 up displacement. 2 over and 1 up displacement. Okay, and on the right are a bunch of other displacements. Every one of those is a 2 over and 1 up displacement. And the point of drawing them all is to say that every one of these has the same magnitude and the same direction. So they are not just a lot alike, they are in fact equal. That is to say, vectors are not located at some starting spot. You can slide it to some starting spot that's convenient, that's great. But you can also place a vector anywhere you like. So these vectors, 1, 2, 3, however many there are, these vectors, every one of them is equal to every other one of them. Okay, and equal to this one besides. So these displacements are all equal because they have each of them the same magnitude and the same direction. That displacements are not anchored at any particular starting spot. And so we're going to, we need to write this stuff down mathematically. So we represent displacements in this way. A vector in 2 dimensions is a pair of reals. I said 2 over and 1 up, and you can see the 2 over 1 up vector right down here. 2 over and 1 up vector right down here. So we denote vectors with an over arrow, and also comment is boldface. I won't use boldface for a number of reasons. Mostly, I find it difficult to write on the blackboard. But anyway, I'm going to use the over arrow, and we'll write the numbers vertically. So the 2 over 1 up vector gets written with a 2 on top and a 1 on the bottom. The 2 reals are called the vector's components. So x is the first component, y is the second component. The 0 vector, just naming a vector that has a name, the 0 vector has components that are both 0. So the 2 over and 1 up displacement on the prior slide is represented this way. We might call it W with an arrow over. All right, and then here is that vector. Since it doesn't have any particular starting point, it's sometimes convenient to move it to start at the origin. That's said to be the vector in canonical position, starting at the origin. Authors typically don't trouble themselves to distinguish between a displacement and the vector representing that displacement, between the thing and the name of the thing. They also don't distinguish between the point xy and the vector that, when in canonical position, ends at that point. So in chapter 12 here, we often will not distinguish between the vector that ends at 2, 1, and which is here, and the point 2, 1. So we'll be a little bit sloppy about it, but it will be very convenient to be so. All right, so we've defined what the things are, and now it's time to define what you do with them. First, I want to make a remark about that definition. So we've defined a way to represent displacements, and we've called those vectors. A vector, I think it's Greek, means something like traveler. So or carrier. So you are somehow related to motion. So next we're going to talk about operations. For example, how do you accumulate? If you have two vectors and you do first the one and then the other, how do they combine? So the right way to think of this is that you imagine that you're walking across the deck of a boat while the deck is moving. So you have a motion due to your walking and a motion due to the boat. So maybe the motion due to your walking is 2 over and 1 up, and then the motion due to the boat might be 1 over and 1 up, and so the total motion combines like that. Now that's what's pictured here. There's a motion, say, due to your walking, and a displacement due to your walking and a displacement due to the boat, and the two combine in this way. Displacement accumulation puts the tail of the second on the head of the first, right there, the tail of the second on the head of the first, and the combination goes from the tail of the first all the way up to the head of the second. Okay? I'm going to observe that accumulation of displacements is commutative because just draw the picture of doing the boat first and then your motion. If you'd done the accounting to account for the boat first and then account for your motion, you would of course end up in the same spot. So accumulation of displacements is commutative. And then I have a comment here. We're going to be defining a lot of things. I want to talk a little bit about what the definitions are. When you make a mathematical presentation, when you're a math teacher, for example, when you make a mathematical presentation, you often strip out a lot of things, and we will start with the definition of vector addition as component-wise. However, that approach is in some way misleading. So we make these definitions to reflect what we're modeling, in this case, the displacements. So we don't define vector addition as component-wise because it's easy or because it's somehow obvious. Instead, we define vector addition to be component-wise addition because it fits what we're modeling, namely the accumulation of displacements. If displacements behaved in some different way, we'd come up with a different definition. We might have some cockamamie definition just simply because that's what it is that we're trying to model. Okay, so when I go to the next slide and it has a perfectly easy definition for vector addition, they're not defined that way because it's kind of the obvious thing to do. They're defined that way because it fits with what we're trying to model. All right, so here it is. It says the sum of two vectors is you add the x's and you add the y's. Then you get the famous parallelogram pattern where if you add vector naught and vector 1 in the order vector naught plus vector 1, you'll get the same result as if you add vector 1 plus vector naught, something that we've already observed. Okay, and I did it down here with algebraically with x's and y's. Okay, or geometrically with the picture. If you take a vector, now that I can add a vector, I could take vector v plus v plus b, and it would be natural to call that 3 times v. It would also be natural to call minus v the vector that additively cancels v, so that if I took v plus minus v, then I'd end up at 0. So the scalar multiplication operation between a real number and a vector acts by rescaling the vector's components. If I want to add the vector to itself 3 times, I expect each of the components to grow by a factor of 3. That's exactly what it says, is that 3v should be make the x's 3 times as big and the y's 3 times as big. Or minus 1, or 1.75, or pi, or whatever you want for the rescaler there, r. Okay, so the scalar multiplication rescales the vector's component. I did addition, I did multiplication by a real number, now I'm doing a subtraction. I mean, you're just sort of ticking through the boxes in this mathematically quick, but I already cautioned you a little bit about the presentation that you can lose sight of the idea behind the presentation. So this vector shows that we want v1 minus v0 to be the vector with the property that if you take v0 and then you combine it with v1 minus v0, then you should end up at v1, at the endpoint of v1. Okay, and that of course fits perfectly well. So v1 minus v0 also fits with the prior slide because v1 plus negative 1 times v0 will give you the same result. That's the geometric picture. The algebraic picture is if you want to subtract two vectors, just subtract their components. Subtract the x's and subtract the y's. So again, there's a sort of a slick definition here that nobody's going to raise their hand and say, why would you do such a crazy thing? But we're only doing it because it fits with what we want to model. So don't lose track between what's behind the definition and how the definition is so easy that a person says, let's keep going, I got this. So practice, time for practice. I urge you, of course, to take out a piece of paper and and try the problems, and then come back and see the answer that I put up. I just have a pile of vectors here. You might notice this vector here is called I, and it is the vector with a 1 and a 0. There's also a j that consists of a 0 and a 1. Anyway, I have a pile of vectors, and I'm going to add a plus b and b plus a. I'm going to give you a second to pause the video and give it a try. Okay, great. A plus b is you add the 1 and the minus 3, and you also add the 2 and the 1. B plus a gives you the exact same thing. A plus b plus d, and contrast that with a plus b, and then later on add d. Okay, please? So if you add a plus b plus d, well, the parentheses tell you to add b plus d first. So b plus d has an x component of negative 3 plus negative 2, and also a y component of 1 plus minus 1. And then a plus b plus d is what it says there, 1, 2, added to minus 5, 0. And naturally, of course, a plus b gives you the minus 2, 3, and the d, and when you combine them all together, they come out to be the same thing, namely the x component is negative 4 and the y component is 2. Okay, next please. All right, an easy one. When you combine d plus 0, you're just simply adding 0 to everything, so it doesn't change that thing. Next one, please. Subtract the components, and you're looking at minus 4 for an x component and 1 for a y component. And then the minus 2 times I. Great, so you just simply multiply all the components by minus 2. Of course, minus 2 by 0 makes 0. And then down at the bottom is a linear combination of the vectors. So 5 of the first, minus 1 of the second, and 12 of the third. And it turns out to give minus 16 and minus 3 for the x and y components. Okay, so the arithmetic is very straightforward, and everybody's going, I got this, but I want to make sure that we didn't define them that way because the arithmetic is straightforward. We define them that way because it models what it is we want to model. The fact that the arithmetic is straightforward is one wonderful side effect. And we get these rules. So vector addition is commutative. We already saw the first. The 0 vector is the additive identity. We saw an example of the second, that if you add something to 0, you get the thing back again, and if you take v plus minus v, you get 0. Addition is associative. It doesn't matter where you put the parentheses. And finally, scalar multiplication respects the vector operations. That is, 1 times a vector is the vector. If you take r times the sum of two vectors, you get r times the first plus r times the second. And if you take r plus s times a vector, you get r times the first plus s times the second. And then finally, if you take r times s times the vector, you get the same thing as if you took r times s times the vector. And because the algebra is so simple on these operations, it's very easy to work through them. I did the example of v plus 0, but the others are no more complicated. Again, taking them through at a reasonably high rate because none of them are sort of mathematically hard. Again, it cautions you that there's an idea behind the definitions, but anyway, none of them is mathematically hard. And to be perfectly honest, most of them are very familiar to most of the people in the room. So the length, or sometimes called magnitude of a vector, it's just its Pythagorean length. We're doing Pythagorean geometry here in the plane. So we use absolute value bars because we tend to use absolute value bars anywhere we're trying to talk about the size of the object. Okay, you can put the absolute value bars around the v, you can put the absolute value bars around the xy column, or you could just take the square root of x squared plus y squared. And I did an example, but it's not a tough example. So I have a vector whose tail is at 1, 3 and whose head is at minus 2, 5. So the tail is at 1, 3 and the head is at minus 2, 5. So So you got to figure out what is the description of that vector first, and then you're going to take the square root of x squared plus y squared. Okay, so if you have a tail at 1, 3 and a head at minus 2, 5, then the change in x is, the change in the x component is to go backwards by 3, and the change in the y component is to go up by 2. And then finding the length is just a question of taking the square root of the sum of the squares. So this gives an interaction of length between the vector operations that we've already seen. That's critically important. Everybody is familiar with this. But the first sentence is that the length of the scalar multiple r times v is the absolute value of r times the length of v. So if you make a vector, if you make the components of a vector twice the original magnitude, if the vector was x comma y and now you make them 2x and 2y, then the vector will be absolute value of 2 times as long. Okay, so that doesn't seem to surprise people. The triangle inequality is the most familiar interaction between length and vector operations. That is to say, familiar to everybody. That is to say that if you take the sum of two vectors and then find its length, that will be less than or equal to finding the length of the first and then adding the length of the second. And the picture shows exactly what's happening here, is that the sum of the two vectors going straight from the start to the finish is less than or equal to going around. Okay, so that's called the triangle inequality because look, it makes a triangle. So I have a comment about the triangle inequality. I mean, I write it on the board and people nod and write it down in their notebook, but I have a comment about the triangle inequality. So the triangle inequality is about something. It says that our familiar Euclidean plane is flat. A space that is not flat has paths where it's longer to go straight from the start to the end than it is to just go around. I have a 3D picture of this. I have a 3D picture of a couple things I want to do today. So let's try the 3D picture. And there's the region. Can you see the region? There we go. And it's got a little mountain in it. Okay? Got a little mountain. The mountain goes up enough that it is longer to go from the start to the finish. You have to walk up and over the hump than it is to go around the mountain. Okay, so the triangle inequality somehow speaks to space being flat. The space that we're working in being flat. If it doesn't have bumps in it, then the familiar triangle inequality holds. Okay, so there's an intuition there. Great. So as usual, like to have folks practice, and so there's a pile of vectors on which to practice. Okay, and I'll pause, give you a second to pause the video and try it on a piece of paper. Great. So the square root of, oops, I said plus, I meant to say comma. Forgive me. Comma. The square root of 1 squared plus 2 squared is the square root of 1 plus 4, so square root of 5. And for b, the square root of minus 3 squared and 1 squared, so that's 9 and 1 makes 10. Okay, and then illustrating the triangle inequality, so the sum of the two vectors, then take the length, versus taking the length and then summing. Please? Okay, so if you take the sum of the two vectors and then find the length, you get the square root of 13, about 3.6. On the other hand, if you take 5, the square root of, the length of A, which we just figured out a minute ago, and the length of B, which we just figured out a minute ago, and that's how you can see the plus from the previous question, it was a typo. The square root of 5 plus the square root of 10, and my computer says that that's about 5.3, so it is indeed bigger. Okay, length of A minus B, just to illustrate a minus. All right, so I calculated A minus B and then found its length. Length of I, here's I, you remember I? I looks a little funny because it's traditional to remove the dot before you put the vector arrow on. Anyway, length of I. Okay, so square root of 1 squared plus 0 squared. Length of 4A plus D. So you find 4a plus d, and you take the square root of the x squared plus y squared. Length of 0. I mean, that's not a surprise. Okay. So again, I expect that for many folks watching this, all of these are familiar, or at least most of them are familiar, but there may be some new things. And then we're just trying to make sure everybody has brought to the front of their mind the vocabulary and the sort of ideas. A couple of things may be new, but probably not many. So here we go, some more vocabulary. Length 1 vector is called a unit vector. And for any non-zero vector v, finding a unit vector in the same direction is called normalizing that starting vector. And you just simply take the vector v and divide it by its length. That is to say, you rescale it by 1 over the length of v. And an example is, I have a vector that starts at 1 comma minus 1 and ends at 5, 4. So to figure out what vector that is, you have to take the endpoint minus the beginning point, 5 minus 1, and 4 minus a minus 1, 4 comma 5, 4, 5. And then to normalize it, I just take the vector and multiply by 1 over the square root of 16 plus 25. Of course, 16 and 25 come from the square of 4 and 5. And it's a 41, so it's not a very nice number. But on the other hand, it has the advantage that a person sees right there where it is and where it came from. Okay, if you have a unit vector in the plane, then you must fall on the unit circle. So somewhere on the unit circle is that unit vector, there's the endpoint. So all unit vectors in the plane have the form cosine theta and sine theta, where theta is a real number of radians. The unit vector in the direction of the axes are called a standard basis vector. So there's the x and y axis, and I need another color to draw them. So if I take a unit vector along the x-axis, that's called I. And if I take a unit vector along the y-axis, that's called j. Another tradition is to call them E1 and E2. I frankly like the second tradition, but calculus books often do the first. Okay, so just building up some vocabulary that we will find handy soon enough. Please practice. So normalizing a gives us rescale a by a factor of 1 over square root of 5. And there it is. The same for the 0 vector. There's nothing by which you can rescale the vector. And in any event, 0 doesn't have a direction, so you can't find a unit vector in the direction that doesn't exist. Okay, so that was a bit of a trick question. Sorry about that. I did want to make a comment. It has been my experience that many folks in the room have used vectors in high school physics or in some other applications. Some folks know an awful lot about vectors by the time we get to this subject in this course. So I just simply wanted to give an illustration for folks who have never seen them before, or have only seen a little bit of them, of the kinds of things that other people have been working on. So I have 2 cables holding up a 100-kilogram weight. So here's a 100-kilogram weight. Here, a little piece of lead there, a little cube of lead. 100-kilogram weight hanging down at W. And what are the forces on the cables? You see they're different angles? Different angles. What are the forces on the 2 cables? So the weight exerts a force downward with a magnitude of 100. We want the magnitude of F1 and the magnitude of F2. And what characterizes what's happening here is that because this picture is standing still, I mean the weight is not dropping to the floor, something the cables are actually holding up the weight. The 3 forces, capital F1, capital F2, and W have to add, oops, I didn't put a vector over W, have to add to 0. So then I want to know, for magnitude times direction, and here I already know for W. So I want to get that they add to 0, 0. Okay, so I decided that I was going to move W here to the other direction of the equation, and so here is F1 times cosine of 125, sine of 125, three decimal places, because come on, I'm just illustrating. Here is F2 times cosine of 30, sine of 30. And here is, sometimes folks ask about how come the 100 doesn't have a minus on it. And the answer is it did have a minus on it, but when I moved it to the other side of the equation, minus became a plus. And it's just a regular linear system, and you solve it, and my computer gave an answer of something like 90 and something like 58. Okay? Okay, so you can use vectors an awful lot in physics. I didn't want to give hundreds of examples, of course not, but I want to give one. Okay, so we've done 2D, so we're moving up to 3D, and again, focused mostly on the vocabulary, but also trying to stop from time to time and point out this is the idea, this is the idea. So in 3D, just like in the plane, you can locate a point in the plane by using 2 coordinates. In 3D, you can locate a point in space by using 3. So I happen to be looking at the point 2, 3, 1. So it's 2 in the x. So in some sense, you go out 2 in the x direction, and then you go 3 in the y direction, and then you go up 1. I suppose if you wanted to, you could go 3 in the y direction, up 1, and then 2 in the x direction. I suppose you could do that also. Okay, in the plane, the axes divide space into the quadrants: first quadrant, second quadrant, third quadrant, and fourth quadrant. 3 space has octants. There's 8 of them. 4 above the xy plane and 4 below. The one shown where all 3 coordinates are positive is the first octant, but the other octants don't have standard names. There's nobody ever says the third octant. There's no sort of convention for what those are. We're still working in some kind of Euclidean space, some kind of Pythagorean space, so the distance between points is the Pythagorean distance, the square root of the sum of the squares. And distance satisfies all the rules that you would think it satisfies. Distance is non-negative. It's 0 if and only if the 2 points are the same. Distance is symmetric, that is to say the distance between P1 and P2 is equal to the distance between P2 and P1. Distance satisfies the triangle inequality that we talked about a few minutes ago, that the distance from P1 to P3 is less than or equal to the distance from P1 to P2 added to the distance from P2 to P3. So it's shorter, or at worst equal to go straight from P1 to P3 than to detour via P2. Okay, and the equality holds if and only if the 3 lie in a line. So we're looking at distance formula. So I'm thinking that we're looking at sort of the regular sort of distance formula stuff. And so I had some trouble there. So we can do things like, instead of a circle, we could talk about a sphere, and I'll go to 3D, and just because I want to illustrate a couple of 3D things here. So this is a sphere, regular sphere, and it is characterized by the fact that every point on the sphere is the same distance from the origin as every other point on the sphere. So x squared plus y squared plus z squared, square root, is equal to r. Said another way, x squared plus y squared plus z squared equals r squared. So if you're on the sphere, then you satisfy that relationship. If the sphere is centered at the point a, b, c, why then if the sphere is centered at the point a, b, c, why then the equation has an x minus a quantity squared, and a y minus b quantity squared, and a z minus c quantity squared. And again, perfectly familiar. In 2D, we work with curves. We draw x-y axis, and we get a kind of a random curve. In 3D, we're going to work with surfaces. So I drew a random surface here. It's a little harder in 3D to draw a random surface because you've just got more going on, kind of thing. And want to emphasize that this is a 3D picture, so I'm going back to 3D. It's too many buttons for me to push, I apologize. Going back to 3D, come on, buttons, 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 there we go, back to 3D. And if I want, I can move that around and look underneath it. I mean, it's a kind of a bumpy space in 3D. I always imagine it being like a sheet, a bed sheet, that's just sort of blowing in the wind. Okay, so there we go. So 2D curves have tangent lines. So in 3D, you won't be astonished to hear there'll be a tangent plane. So I might have a point and there'd be a tangent plane. Okay, you can imagine a piece of paper that you've kind of snugged up to the surface. Instead of area under the curve, we'll find that we have a volume under the curve. Volume under the curve. Excuse me, volume under the surface. Okay, please practice. Okay, and we're looking at the point 4 comma minus 2 comma 3, and it asks how far is it from the xz plane. Sometimes with these, people initially at least have some trouble picturing 3D. So 4 comma minus 2 comma 3, 4, there's 1, 2, 3, 4. Minus 2 makes it back by 2, and then 3 makes it up by 3. And it says the xz plane, so maybe I'll have a different color for the xz plane. There's the xz plane. How far is it from the xz plane? So the answer is its distance is the magnitude of its y coordinate. Okay. So the absolute value of minus 2. Which of the 3 points, 2, 3, 1, etc., is closest to the yz plane? And I'll give you a second. So the one with the smallest absolute value of its x coordinate. So the smallest absolute value between the absolute value of 2, the absolute value of minus 3, and the absolute value of 4. So of course it's the 2. What surface is described by the equation y equals 2? So what's happening here is that it's making us think about, oops, forgot to change the color back. There we go. So it's making us think about what equations mean. So an equation is a criteria for membership in the surface. So there is the surface y equals 2. It's all the points whose second coordinate is 2. So, 1 comma 2 comma 7, 0 comma 2 comma 5. Okay, so it's a plane. Sketch the 3D surface described by x squared plus y squared equals 9. Okay, and what's happening here is that we don't have a z coordinate. So what does that mean? Does that mean z equals 0? No, it means z is unrestricted. What's the criteria for membership in this surface? It is that x squared plus y squared equals 9, and there's no restriction whatever on z. So there's some relationship between the x's and the y's, but z is just whatever z wants to be. If x equals 3, y equals 0 works, as it does, then x equals 3, y equals 0, z equals 5 works. So does x equals 0, y equals, so I said that wrong, x equals 3, y equals 0, 5, x equals 3, y equals 0, minus 2, x equals 3, y equals 0, 29. All of those points are going to be on that surface because the criteria is met. X squared plus y squared equals 9. There's no restriction on z. Okay, so we're looking at a cylinder of radius 3 that's wrapped around the z-axis. So in the too many colors in 3 space. Here's the xy plane, and we know what x squared plus y squared equals 9 looks like in the yz plane. It's a circle. Apologies for the difficulty drawing the circle. There we go. When you put no restriction on z, if this is a perfectly good point with a z coordinate of 0, it's going to be a perfectly point with a z coordinate of 1 or 2 or 3 or 4, etc. Minus 1 minus. That is to say that what we get is a cylinder that goes up and down, unbounded in the z-axis, wrapped around the z-axis. For any x comma y point, you can have whatever z you like. Okay, equation of the sphere with radius 4 and center 1 minus 3, 2. What's its intersection with the yz plane? So the equation is just take the x minus 1, quantity squared, y minus a minus 3, quantity squared, z minus 2, quantity squared, and it's supposed to have radius 4, so it's 16, r squared. And then the yz plane is the place where x equals 0. So if x equals 0, then you just are looking at y plus 3 squared and z minus 2 squared equals, oh, why does it say 15? Oh, just a mistake. I apologize, just a typo. That's even dopier than my usual typo. I apologize. There we go. Okay. So the equation x squared plus y squared plus z squared equals 6x minus 4y plus 10z describes a sphere and finds its center and radius. Okay, and this is going to be a complete the square one. So we've got x squared minus 6x, y squared plus 4y, z squared plus 10z. And when you complete the square, x squared, you're looking at completing the square. X squared minus 6x plus 9 is x minus 3 quantity squared. Y squared plus 4y and then plus 4 is y plus 2 quantity squared. Z squared plus 10z plus 25 is z plus 5 quantity squared. I ended up adding 9 to the left side, 4 to the left side, and 25 to the left side. 9 and 4 and 25 makes 38. So in order to get the equality to stay equals, I had to add 38 to both sides. So I got a center of 3 minus 2, 5. The 3 came from that this is x minus 3. The minus 2 came from that this is y plus 2 quantity squared, and the minus 5 came from that this is z plus 5 quantity squared, and then the radius has got to be the square root, and 38 is just what worked out, so its radius is the square root of 38. And then the last here, do the points given lie on a line? Okay, and the answer is yes, because a lot of times folks don't know that the triangle inequality also works in reverse. The theorem says it does, but anyway, the triangle inequality also works in reverse. That is, if you take the length of AB plus the length of AC, if it adds to the length of BC, that means that the points all lie on a line, that the shortest distance between B and C is to go via A, so they lie on a line. So one kind of takeaway to me from this practice is that for some folks, for many folks, maybe not all, but most folks, when they first start thinking about 3D, it's a little bit of a stretch to kind of close their eyes and think carefully about what's happening. 2D is so familiar, so that the purpose of these exercises really was to give a person a little sense that there's going to be some growing happens in changing from 2D to 3D. The mathematics isn't especially harder, it's just that there's some sort of close your eyes and think about that has to happen. Okay, so that leaves me with, I've done points in 3D, and now I'm going to talk about vectors. So the vector in 3 dimensions is just a generalization of the vector in 2 dimensions. You go from the head minus the tail in the x-coordinate, and then the y-coordinate, and the z-coordinate. And again, some authors use boldface, and I will not. Vectors add, subtract, and rescale component-wise in the way that, at this point, having seen 2D, nobody is astonished by. The length is the regular Pythagorean length, the square root of the sum of the squares. And the standard basis vectors, instead of being just I and j, are I, j, and k. Okay, and the E1, E2, E3 is what a person might also use them. I, j, k is what you often see in calculus, but you can see the limitations of I, j, k because you're going to run out of letters at some point. E1, E2, E3, you never run out. The vector in n dimensions is just exactly the same thing. The other ones were 3 tall, this one is n tall. All the natural extensions from 2 dimensions and 3 dimensions all hold, including that vectors add, and for example, the vector addition is commutative, length is Pythagorean, and every entry of the zero vector is 0, and etc. So there are the rules. Addition is commutative. Zero vector is the additive identity, addition is associative, scalar multiplication, and the rules for lengths are the same. And you might even remark to yourself that this is the same, the text here, not the three-dimensional picture, but the text is the same as the text was for 2 dimensions. Okay, so what you have really is a system that continues to hold when you move to higher dimensions. All right, so you have, you can sort of say, in general, when you look at vectors, you're looking at such and such a thing, and that's the study of vectors then is called linear algebra. Okay, some practice. Just straightforward arithmetic. I hope I got it right. Just straightforward arithmetic. Length of this vector. Again, just straightforward arithmetic. and normalize. Normalize means turn it into a vector with the same direction, but whose length is 1. Okay, so you have to divide by the square root of minus 2 squared plus minus 2 squared. So divide by the square root of 8. Rescale the vector by a factor of 1 over square root of 8. Okay? Okay, very good. So that ends the introduction, and I think it's the case that, as I promised, it's a lot easier than the stuff we've been doing. So that's nice. It's nice to have a little bit of a break.